Welcome to the first video of Electromagnetism course in Chapter 1, Vector Algebra. Now, in this course, we'll be talking about a lot of different quantities. There will be two types of quantities throughout this course that we'll be talking about. The first one will be a scalar quantity, and the second will be a vector quantity. Now, what's the difference between a scalar and a vector? Now, a scalar is a quantity that only represents a magnitude, like time. Time is a magnitude quantity. It only tells us how many seconds are there in this specific quantity. When we say, I'll be there in 10 seconds, you know that 10 seconds needs to pass for me to be there. And that's all there is. How much of that unit is there in that time or in that, value. However, in vector, there's an additional information that is portrayed when we talk about vector, which is a direction. For example, in scalar, we use distance when we talk about the distance between two objects. For example, these two are 1 meter apart. Now that's a scalar quantity. There is 1 meter between them. However, as a vector, when we add a direction, we say the red pencil is 1 meter away from the black pencil to the north. Then we know where that object is. We know how far it is, and we know the direction of it. We know where it is located with respect to the black. Thus, it stops being called a distance. It becomes displacement. Because distance is only a scalar, while displacement has both magnitude and a direction, it is a vector. And we represent the vector by an arrow. The longer the vector, the more magnitude it has, and the pointy side of the vector represents the direction of the vector. So we can say, for example, this vector has 5 Newton of force, and this vector could have 10 Newton of force, and they are both to the right direction. There's a third definition I would like to add, and the definition is a field. What is a field? A field is a function that specifies a particular quantity everywhere in a region. And what does that actually mean? Let's say that you have a room and you want to know the temperature in a room. You can say, oh, the room temperature is 30 Celsius. But that just tells you the average of everything in the room. But you can also do a distribution of the temperature in the room that shows you the temperature everywhere in this room. It would look something like this. You have a room, and it would say, for example, oh, here it is cold, and here it gets hot. And there's a slow transition in between. I don't know what do I put in the middle. Now you know more details about the temperature in the room. This could be This could be 10 Celsius. This could be 20 Celsius. This could be 30 Celsius. Now this is a field, a temperature distribution. And since it is just random, now we'll see what's more specific. Maybe random is the wrong word, but this is a scalar field. By that, I know in the 10 Celsius that in this region is 10 Celsius. In this region it's 20 Celsius, and in the third region is 30 Celsius. There's also a vector field, which would look something like this. Now, temperature by itself is scalar. So when there's a field that represents temperature, it's a scalar field. But if you want to put a vector field, we need to represent a vector quantity. For example, velocity. We know that the velocity is a vector. It has the speed and the direction of that speed. So we can say the direction or the velocity of the raindrops on a rainy day. So let's say there's a cloud here, and there is wind in this direction, blowing them away. We can put or represent the direction of the raindrops by multiple arrows. Something like that. And that is a vector field. It's a region that tells you a particular quantity, which is in this case the velocity of the raindrop. Now, mathematically, we represent the vector by a letter that will symbolize the vector, and a small arrow on top of that letter. The arrow will tell us it is a vector. Without the arrow, it could be a scalar. We don't know, but it's not a vector. In some books, they do small, like normal A for a scalar and bold A for a vector, but I'll do the arrow symbol because it's easier to write on a paper. Now, a vector, we said it has two parts. It has the magnitude part, and it has direction. Direction of the vector. To have a symbol for the magnitude, we put it between two lines. That is the magnitude of this vector. And the direction is in a small a and the letter of the vector beneath it. Now we know that there's this unit vector. A magnitude is just a value. It doesn't need more explanation. It's only a value of that vector. But the unit vector, which is this, well, it's a small vector that has a magnitude of 1 and has the direction of the main vector. So a unit vector has a magnitude of 1 and the direction of the main vector. It is also dimensionless. Well, it has no unit. That's what dimensionless means. It doesn't have Newton, seconds. It's just an indication that tells you the vector is that way. And we know that the main vector is equal to the magnitude and the direction. So we just multiply them together. A small of a. Notice that there's a tiny arrow above the unit vector because it is a vector. Thus, we can say, well, a, the unit vector of a is equal to the vector divided by the magnitude of it. In the xyz plane, a vector is written as ax multiplied by the unit vector of x plus ay multiplied by the unit vector of y plus az multiplied by the unit vector of z, and then we add the arrows. Now these ay, az, ax are the components of the vector. We have the ax is the x component of the vector, the ay is the y component of the vector, and the az is the z component of a vector. And these are the unit vectors. As you can see, there's an x, hence to the x direction, a y to the y direction, and a z to the z direction. And this is in the x, y, z plane, or the Cartesian coordinate. Now, the magnitude of the vector is equal to the square root of ax squared plus ay squared plus az squared. Now, to explain this further, let's say you have vector A. Now this vector has a component in the x direction and a component in the y direction. It's in the 2D, two dimension. And as you might notice, this is a right triangle. What would A equal to? Let's say this is AX and this is AY. Well, we would say that according to Pythagorean Theorem, we would say that A is equal to A squared plus AX squared plus AY squared. Add the square root, and thus you have A is equal to AX squared plus AY squared under the square root. And that is the magnitude. That's how long this vector is. And that is the magnitude. It's how long the vector is. And in the third dimension, you just add the third vector. And to find the value of the direction, well, you might have noticed that it's the unit vector. And we know that the unit vector is equal to the vector divided by the magnitude. If we substitute the vector and the magnitude, we get that it's equal to AX plus AY plus AZ divided by the square root of AX squared plus AY squared plus AZ squared. Excuse my handwriting, I'm still getting used to the digital thingy, and it's not as good as the paper. Nothing feels as good as the paper. If we have an XYZ coordinate, XZ, oops. Okay. The direction of the AZ would be here. This would be AZ with 1, and this is the AX with the value of 1, and this would be AY. Now let's review everything we've said so far. A scalar is a quantity that only has a magnitude, and a vector is a quantity that has both magnitude and a vector. Thus, the vector has more information than a scalar. A field is a function that specifies a particular quantity everywhere in a region. We've said that a field can be a scalar if it represents a scalar quantity, and if a field can be a vector field, it represents a vector quantity. And a vector has both magnitude and direction. The magnitude of the direction, we just call it the magnitude, and the unit vector represents the direction of the vector. Also, the unit vector has a magnitude of 1 and is dimensionless and has a direction of the main vector. It is also a small vector. The vector is mathematically it's equal to the magnitude of itself multiplied by its unit vector. We also represent the vector is equal to the component of AX multiplied by the X unit vector plus the component of the Y direction multiplied by the Y unit vector plus the Z component multiplied by the Z unit vector. And to get the magnitude, you square root the sum of each component squared. And to get the vector, you divide the main vector by the magnitude, and you would get the vector.